The Sun is the most important star in our system, and its gravity is responsible for having all planets circle around it. The Sun energy power is indisputable and affects our planet in many ways. This energy can be seen as the Aurora Borealis, or the Northern Lights, or the Aurora Australis. The beautiful lights which appear respectively in the North Hemisphere as well in the South Hemisphere. Watching the auroras, we may think, what is the relationship between the Sun and such a beautiful event? Or we even may ask, could they cause any harm to our lives on Earth? The answers for these questions comes from many years of observations, researches, and analyses of data. The results of these studies came up that the Sun is the source of power to produce such an event. More precisely, the solar's eruptions produce what we call CMEs, corona mass ejections, powerful electrical winds that leave the Sun after explosions or solar flares which occur on its surface. And these waves of energy travel through space in a direction towards the Earth, touching our magnetic field and producing a disturbance in it. Each time the Sun's radiation touches our magnetic field, it breaks down, making the two separated parts reunite at the other side of Earth, allowing the electrical particles from the Sun's radiation get into our atmosphere. These electrical particles from the Sun can cause damages in various ways, bringing consequences to our life on Earth, and also cause a beautiful effect known as the auroras. It's so much to say, to observe, to study, so much to discover. Originated at both poles, after Earth being touched by so powerful of an energy, an effect that can be seen at Northern Hemisphere in Alaska, Canada, Greenland, Northern Scandinavia, and Russia, and at Southern Hemisphere by the oceans, which circle Antarctica, and sometimes even at Chile, New Zealand, and Australia. But would the rest of the world be able to witness this fascinating phenomenon? Would such a beautiful sight have any bad consequences if we were able to see it here? Those are some questions that we would need to add to our concerns. Could it cause any harm to our lives on Earth? This Sun radiation that we see as such beautiful lights, could they have any effect in our lives? The damage from the Sun's geomagnetic storms happen more often than we can imagine. From minor interruptions in low-frequency radio waves to major disruptions in our power grid, our lives are affected. NASA and NOAA are responsible for the Sun and space-based monitoring of space weather. On Earth, it is the United States Geological Services that monitor space-based weather from the ground. A network of magnetic observatories are stationed across the United States and throughout our territories on the Pacific and Puerto Rico. Real-time data is available to industry and private entities. Mapping of the geomagnetic hazards is important for the electric power grid industry and our own well-being. NOAA's space weather scales describe the environmental disturbances for 3 types of events, ranging each from 1 to 5 in intensity. Radio blackouts take the least amount of solar radiation. The minor R1 tier of the scale has the ability to cause minor degrading in HF radio communications and loss of low-frequency navigation signals, such as LORAN, for short periods of time. The extreme R5 tier has the ability to cause high-frequency radio blackouts for hours, resulting in a loss of HF radio contact with mariners and aviators in this section. The solar radiation storms have little effect on the minor S1 tier of the scale, but move progressively higher in the amount of degradation and damage they can cause. During strong S3 storms, astronauts should avoid high peculiar activity such as spacewalks, and passengers and crew in high latitudes could be exposed to radiation risk. Satellite operations can experience a disruption in imaging systems. R3 storms can also degrade high-frequency radio through the polar regions and navigation position errors. The most extreme S5 tier can leave astronauts on EVA and passengers and crew in high-flying aircraft at high latitudes with exposure to radiation risk. Satellite operations could be rendered useless. Memory impacts can cause loss of control. Star trackers may be unable to locate sources, and permanent damage to solar panels are possible. Other systems affected could be the complete blackout of high-frequency communications through the polar regions, and position errors can make navigation operations extremely difficult. Geomagnetic storms are the most powerful and potentially damaging space weather. They can affect power systems, spacecraft operations, and migratory animals. Sensitive animals and birds can feel the effects of geomagnetic storms at these levels of space weather. The effects of a minor G1 may not be apparent, such as a weak power grid fluctuation. The aurora is commonly visible at high latitudes such as northern Michigan and Maine. On April 27, 2017, the geomagnetic storm scale reached a G1 with no reported interruptions in satellites or the power grid. On April 24th, a moderate G2 storm occurred. The aurora could be seen as far south as Colorado. Voltage alarms could sound on high-latitude power grids. The effects of the storms are getting stronger with the increased size of the solar flares on the NOAA scale. The last strong G3 storm to be recorded was on May 8, 2016. False alarms at power systems and voltage corrections could be required. High-frequency radio could be intermitted, and satellite navigation and low-frequency radio navigation problems could occur. There is a possibility of the aurora being seen as far south as Alabama and Northern California. It was on March 10, 1989, that a massive explosion on the sun launched a flare in the size of over 3 Earths in diameter. By March 12th, it struck Earth's magnetic field. This was the last G5 storm to encounter Earth, leaving widespread power outages in Canada and some in the United States. The storm caused electric currents to flow in the ground throughout the continent. By March 13th, the currents in the Earth found their way into Subsitory in Montreal, Quebec, sending it through the whole grid of the system. While Quebec spent the night in darkness, the Aurora Borealis could be seen as far south as South Florida, leaving some to believe they were under nuclear attack. As we saw, the sun takes an important part in this event. The aurora's beauty has been noticed and written history as far back as 2,300 years ago. It is said that after seeing the curtains of light in the sky, Aristotle called the phenomena by chasmata, signifying that cracks in the sky were allowing light from beyond the heavenly sphere to come in. In 1230, a book entitled The King's Mirror used the words northern lights for the first time to describe the aurora. The name Aurora Borealis, as we know today, has some controversy in regards to its creator. Some people say that it was Galileo Galilei in 1619. He named Aurora after Roman goddess of dawn and Boreas after the god of the north wind. Others say that it was the French astronomer Pierre Gassendi in 1621 who gave the name, also after the same two figures. It's also known by other names, as the Cree Indians call it, the Dance of the Spirits. Without caring much about the name, the beauty is indescribable. It was during the Middle Ages when the phenomenon was taken as a bad omen. In December 1719, when the first recorded sighting of the Aurora Borealis took place in New England, people who witnessed its appearance related it to impending terrible catastrophes which would come. But after seeing its currency, they saw it through another view. Awe. But such beauty brought curiosity to scientists, and it was in 1899 to 1900 when the Norwegian scientist Kristen Birkeland was responsible for explaining the phenomenon of the Aurora Borealis in detail. On doing so, he accomplished two scientific feats by inventing the Birkeland-eyed process and the electromagnetic cannon. His theory for explaining the aurora states that the sunspots on the sun shoot out energy electrons toward Earth, and then the geomagnetic fields guide them towards our polar regions, causing the aurora. A series of expeditions called the Norwegian Polar Expedition took place, and he compiled the data of the magnetic field from the high-latitude regions, which led to the entire polar region's electric current pattern to be finally explained. The studies about the aurora's phenomenon went further, and now we know that such beautiful colors that can be seen in the sky during dark nights are coming from the charged particles in solar winds, which collide with atmospheric atoms and ions. These collisions cause the electrons of the atmospheric atoms to become excited. When the electrons return to their original energy levels, these atoms emit visible light in various wavelengths. The Earth's atmosphere mainly contains oxygen and nitrogen. The atoms of oxygen and hydrogen are located in various altitudes in our atmosphere. As the wavelengths change colors, it will depend on the altitude which the greatest concentration of these atoms are. The atomic oxygen emits green lights at wavelengths of 557.7 nanometers, which originate at altitudes of 120 to 180 kilometers. The red is at wavelengths of 630 nanometers, at higher altitudes on the northern hemisphere. The atomic nitrogen causes deep red and blue hues. Blue and violet occurs at altitudes of below 120 kilometers, while red colors can occur at 90 to 120 kilometers. This creates the colors we see in the sky during the auroras phenomenon. But the auroras phenomenon brings other surprise and amazement, as it's seen in the dark skies, floating or dancing with the wind, changing shapes. 5 different forms of the auroras have been presented. They are rayed arc, long, narrow arcs of light, most often ranging in the sky from east to west. Dual bands, curve, wrinkle, and twirl, or even crimp like curtains. Rays, spreading out multicolored like vertical spillways of light that stretch far up in the sky. Corona, the most spectacular form of rayed aurora, developing overhead with all gleams joining the center point. Patches, fluffy, flaming clouds of light, which can generally be seen later in the night. They move as if they were dancing, changing their forms and shapes, giving life to the skies. In the cold nights, on extreme north and south hemispheres, the auroras also sing. The sound of the auroras is produced by charged particles trapped in a layer of the atmosphere on these cold nights, which rapidly discharge when radiation from the sun slams into the earth, producing clapping, radiostatic, faint crackling, light rustling, or hissing sounds and other noises. Now, let's hear the song of the auroras. The intriguing sound which comes from the skies.